I would say mostly tools, computational tools and technology coming from electrical engineering. So I guess this makes a connection to this, a good connection to this conference. So first of all, I would like to acknowledge the hard work of two of my collaborators, ex-collaborators in my research group working on this topic. Dr. Bamru Tausia-Sakul, now with Srinagar Virod University. He has been working as the postdoctoral fellow funded by UPSRC grant in the UK. And Kyriaki Gokci, now with, she has just received her PhD last month working on this project, and she has been supported by City University scholarship, and now she's working in a big consulting company in London. So I guess I have to acknowledge the support of funders and people that made this work possible. Now, I would like to spend some part of this presentation discussing structural health monitoring of civil engineering structures, because this normally doesn't fall within the agenda of electrical engineering. Then we will be looking at a method for damage detection that we have developed for supporting energy efficient wireless sensors, as well as another method we have developed that looks beyond sparsity. So the first method we will be using standard compressive sensing that requires sparsity conditions from signals. The second method, we go beyond sparsity. So we are looking at a method that is essentially signal agnostic. And we'll be looking into several different applications just to make this talk more pleasant. So some facts of life: long-span bridges, tall buildings, offshore platforms, wind turbines support our civilization today, and especially in developed countries, our infrastructure is growing old. So we do need to have an idea of how much time is left in our structure until we upgrade or we replace our structure. Newly built structures are becoming more and more complex. And that means that our computational models that we use during the design may be much different from the as-built structure. We are not in a lab, we are not in a factory doing very precise design of our structures. We are in the field, we're talking about large-scale structures, so we see all sorts of differences during construction from what the structure was supposed to be. So another issue, another motivation why we need to monitor our structures is what's happening after extreme events, earthquakes, traffic accidents. Is the structure working as before? What is its structural integrity level? And so on and so forth. So we do need to develop reliable and cheap tools for monitoring civil engineering structures, just like we need to monitor our human health, let's say. So we'll be looking into one specific way of monitoring structures, and that is through vibrations. My specialty in structural dynamics, so I mostly care about vibrations and vibrating structures. So it is a cheap method because we don't have to close down any structure we want to monitor. Through unmeasured forces coming, depending on the structure, coming from the action of wind, of waves, our structure is vibrating. And if we install, let's say, standard MEMS accelerometers, we can measure the acceleration. So in terms of, let's say, structural dynamics, or even if you want filtering in electrical engineering, we have a vibrating, linear, multi-degree of freedom structure with a lot of states. Our input is, we can assume that it's white noise, and our output is going to be a random field, and we are looking at response accelerations, and the question is, what do we do with them? One way of now interrogating our data is through what we call data-driven damage detection, and this is where all sorts of machine learning techniques, soft computing, find applications in structural health monitoring. So we go and develop some damage-sensitive indices which may not have any physical meaning about our structure, and then we apply detection techniques, essentially comparing a healthy state with a damaged or potentially damaged state, and trying to see how these sensitive indices have changed and what does this mean about our structure. The other big genre that we are looking at is we can do system identification. We can find structural properties like mode shapes, vibrating mode shapes, natural resonant frequencies. Through output-only system identification, under the assumption that our input is just white noise, and from there we can do damage detection through physics-based now indices. Okay, so not just any sort of heuristically defined damage index, something that is meaningful, means something in terms of structural mechanics, or we can also do computer model updating. Okay, so we can go back to our computational model, finite element model, and update it. So we'll be discussing a little bit about this area, so that would be our first application, and then we will focus on this one and try to do damage detection through operational model analysis in this talk. I put together this small slide just to give you an idea of what we mean by vibration and vibrating modes in structural dynamics. So let's say we have a beam heavily instrumented with accelerometers and excited by white noise. This beam is going to be vibrating. If we take the, let's say, the Fourier transform of what each and every one of these accelerometers is measuring, we have this frequency domain representation. The peaks, the location of the peaks gives me the resonant frequencies of my structure, which is very important in design. We want to avoid resonate, and so we want to avoid excessive oscillations. At the same time, if we do this spatial analysis, this will give me the peaks of the different Fourier transforms, will give me the vibration modes, how my structure is going to purely vibrate under, if it is excited under a particular frequency. So, starting with the finite element model, we have usually a mass matrix M, a stiffness matrix K. U is our displacement, and U double dot is our acceleration vector, excited by some external force. That's our model analysis in mathematics, mathematical form. It's an eigenvalue problem, and all we have to, and these are our mode shapes and our natural frequencies. And for linear structures, the response be simply given as a superposition of these mode shapes times some time-varying structure. So my point here is that by knowing mode shapes, by knowing natural frequencies, I can go back and update my mass, stiffness, and perhaps damping matrices. And through this, this is all I need to know about my structure. So, wireless sensors are, we believe that it's the way forward to monitor large-scale civil engineering structures. And that's because, as it has been pointed out in the first paper that really looked into and considered using wireless sensors instead of cable sensor to monitor structures, it says that most of the cost in installing in a large-scale, let's say, building structure a monitoring system comes through cabling. So why not we use wireless sensors? Still, after 20 years now, there are open issues, a lot of open issues, and wireless sensors are not commercially available for structural health monitoring currently. And that is because we have issues with energy sustainability and bandwidth limitations. If we consider that in bridges of this scale, we have hundreds of sensors monitoring 24 hours. The response of the bridge to all sorts of ambient noise. We do need energy efficient sensors, and this comes from minimizing the transmission of data. So what is currently the state of the art, at least in practice, is that we do conventional sampling, usually at rates much higher than the Nyquist sampling. And then locally at the sensor we do data compression before transmission, and then at the base station we reconstruct back our signal. So what we are looking at is whether we can exploit recent or developments happening in the past 10 years in the field of compressive sensing, and to replace all those boxes that we currently have with an analog information converter. So essentially try to do sub-Nyquist, non-uniform in time sampling. So we do data compression and acquisition at the same time in one step, hoping to come up with a more energy efficient sensor that does not consume so much energy. So a few words about compressive sensing in a nutshell. The idea is that if you have a signal, or if you project the signal into a sparsified basis, now this is vectorially seen as a matrix here, so we have a sparse signal, meaning a vector with many zeros and just a few non-zero elements, or elements that are above some specific, relatively low threshold. Then, through a sensing matrix that is usually random, through a sampling matrix, can I retrieve those non-zero components by having just a much smaller number of measurements, m, compared to the length of this vector n. And this is, of course, require the solution of an underdetermined system of equations, but loads of through theoretical advances, we now know that by satisfying certain conditions with great probability, if, for example, and for specific sampling matrices, essentially this comes up to being a random sampling below Nyquist frequency techniques, then we can retrieve the sparse signal by solving a minimization problem. And there has been a lot of research on looking at what is called sparse reconstruction algorithms to solve these kinds of problems. Now, an application, a very recent, this comes from, there's a handful of groups, research groups in civil engineering that are looking into these aspects these days. And this is the first field deployment of compressive sensing-based sensors to monitor a particular bridge, where essentially they do random sampling, and using a particular reconstruction algorithm and a frequency domain decomposition, we can get the modes of vibration and natural frequencies. Now, they are reporting that they can go up to 80% data compression using compressive sensing techniques. So this is for modal estimation. This is the particular algorithm they have used. Of course, there are many more, and perhaps this is one of the earliest algorithms for sparse reconstruction, but advantages and disadvantages are shared by all these algorithms. So they can denoise measurement errors, so errors that go are inside the compressed measurements. They, however, they are not good to deal with noise to the signal that ruins the sparsity, essentially. The other issue is that you need to know in advance, to some extent, what is the sparsity of the signal, so that you can choose how fast you're sampling, okay? Now, these are disadvantages, but still it works well. So let's look at a particular example of a data-driven, let's say, damage detection method that we have developed. We are using what is called the relative wavelet entropy index, which essentially comes up to wavelet transforming our signal, finding its energy between healthy and damaged state, and then compare the differences. And if we see differences, this means essentially that there has been a change of the location of our resonant frequencies in our structure, which essentially means that most probably there might be some damage. Though, of course, these kinds of changes may be due to humidity, maybe due to temperature, but we usually monitor humidity and temperature as well, and so we can decipher whether what we see in terms of different properties is about differences in the environmental conditions or comes from an actual damage. So our aim here, our contribution here, was to use this damage sensitive index and see whether we can come up with a compressive sensing based approach for that, so that we support more energy efficient wireless sensors. So we had to first of all look into our signals in structural dynamics and wavelet transforming them, and we wanted to use a discrete wavelet transform such that energy is preserved, and through filter bands we can quickly even if in decentralized wireless sensors, we can quickly check this, the wavelet transformations. The other issue is that usually the classical discrete wavelet transform, as you are scanning and you want essentially to see what is the distribution of your signal energy in time and in frequency. As you are looking at higher and higher frequencies, you are losing resolution. Okay, and this is we're losing the ability to discriminate essentially modes and how the modes change in the frequency domain. And this is something that we don't want. This is the so-called constant Q analysis, where the central frequency of your wavelet and the bandwidth remains the same. So we don't want that. We want to maintain the same, if possible, resolution as we are looking at higher frequencies. So I have some typical filter bands that currently are being used for structural health monitoring, and what we see is that they have a constant Q analysis. We also see that between different scales we have a lot of overlapping in the frequency domain. Now we don't look a lot into the scales, we want to look into frequencies, because in structural dynamics frequencies have a physical meaning, and this is what we are after. So we see a lot of overlapping between adjacent scales, and we don't want to have that. So we considered what we call harmonic wavelet filter band, where essentially it's ideal filters stacked in the frequency domain, and their bandwidth we can control. So we can come up with a non-constant Q analysis and no overlapping. So let's look at an example. So this is a space brass. It can be a part of, let's say, a railway bridge that's in a healthy state.